Okay, so we were working on pages 9 through 13 on Thursday. 9 and 10 were pretty much doing the same things. The only thing that was different was what type of boundary we had. So here we have two continental crust pieces here. Couple things to notice is this is a convergent boundary, so they're obviously crashing into each other. If you're drawing convection cells, you're going to know that the arrow on the top part is going to go the same direction that the plates are moving, because that's going to drag it that way. And if you have two continental crusts colliding with each other, one of them's not going to go back into the middle of the earth. It's not going to subduct or slide under. Since they're the same density, because they're the same crust and they're also pretty thick, they just end up smushing together, piling together, and you form mountains. Okay. Another thing that is worth pointing out here briefly is oceanic crust can be directly attached to continental crust without like a break in the plates, meaning there isn't a plate boundary here. This would be like all along the eastern United States where the Atlantic Ocean is. It goes right from the continental, like Virginia and South Carolina, and it goes right into the ocean. And there's no break there, there's no boundary. That's why we don't have earthquakes on the eastern part of the United States. There's no plate boundary there. Okay. Then if we go to some of these oceanic crusts, so this was the one I described in the video the other day, and I went into that pretty detailed there, but when we have oceanic crust hitting continental, or oceanic crust hitting anything, one of the crusts is going to go under. Oceanic crust is definitely more dense than continental crust, so oceanic is the one that sinks under. That's what forms the volcanoes when the magma melts, or the rock melts and turns into magma. Okay, and that's where we form a trench. We also form a trench on this last one too. So we have old ocean and young oceanic crust. If they butt into each other at a convergent boundary, you're going to have one of them going under, and it's going to be the older one. So if you remember back to seafloor spreading, when we talked about where the warmest part of the crust was, where the coldest part was far away from the ridge. So if you have older crust that's farther from a ridge, it's going to be cooler. Cooler things are denser, just like these convection cells. The cooler magma sinks, the warmer magma rises. So when the same concept applies here. Old crust, because it's cooler, is going to be the one that goes under, the one that subducts. Okay. So we still form a trench because we have one plate sliding under another. That forms a really deep part in the ocean. The one that goes under also melts, and we form volcanic islands. So the Aleutian Islands that kind of come off of Alaska, that whole little arc that goes off of it, that's all created because one ocean plate is sliding under another oceanic plate. Not because it's going under a continent, but all those islands are volcanic. It creates an island arc, they sometimes call it as well. And that's an example of where this is happening in the Earth, at least, is on the Alaska Aleutian Islands. Okay, the second page, we get out of the convergent boundaries and we start looking at divergent. One that we haven't spent too much time on, this is actually what's going on in the Horn of Africa, which I might have mentioned in class before we got into this whole e-learning thing, is we have a rift valley forming there. That's where Africa is actually getting pulled apart at the horn of it. And when it gets pulled apart, I drew it kind of how it looks. I looked it up on the internet too, just to make sure I was drawing it right. But these chunks of rock kind of just slide off, and you end up with thinner and thinner and thinner sections in the middle. Eventually, if this gets thin enough, you would have obviously an opening where magma can come up. You might have the ocean come over it or water gather here, and you would eventually form a mid-ocean ridge, or an ocean ridge at least, because you'd have magma come up and it would form basalt, which is what oceanic crust is made out of, that stuff. Okay, so then a divergent, when we have oceanic crusts splitting apart, moving away from each other, you have that little tiny mid-ocean ridge. I drew the north and south magnetic signatures or characteristics of the crust, like we did when we did seafloor spreading, just to let us know that that's what's going on here. And we have this black, which represented northern polarity. The magnetic north is in the North Pole. That moved down a little bit, and so did this single line, so did the chunk at the end, and we had a magnetic reversal there. Right. Then the last one is going to be the simplest drawing. About the only thing that you could have done to make this maybe fancier is, like I've seen some of them on Google Images where they have a road or a river, something that usually would just go straight across. And if the fault moves, then you're going to not have those line up anymore. So a fault, a transform boundary, is just where one plate slides past another one. They aren't going into each other, they aren't going away, they just slide past. Okay. But the only other thing that may be worth mentioning here is, we on our map the other day, we looked at a lot of earthquake data, and we've talked about how volcanoes form where one plate slides under the other, it melts, some magma comes up, and it forms volcanoes, or the mid-ocean ridge has volcanoes in it because when the crust opens, obviously magma comes up. But we haven't really talked about earthquakes, if I remember correctly, but any of these boundaries you can have an earthquake form. Doesn't matter if it's a divergent like we have for the ocean ridge, doesn't matter if it's transformed, doesn't matter if it's convergent. They're all going to form volcanoes, they're all going to form earthquakes. So what we want to know there is if we just go with the transform boundary where these two slide past each other, it's obviously these aren't going to be perfectly smooth surfaces where it's easy to slide past. You're going to have lots of little bumps, cracks, dirt, rocks that are going to kind of catch, and even though you're putting force on it and it might not move for a while, eventually you're going to have so much force that it just suddenly moves. And that sudden movement obviously is going to shake the earth. It's going to release a lot of energy. The faster that movement happens, or the bigger the movement is, the stronger your earthquake is. Okay. So you can have some pretty strong earthquakes on transform faults, transform boundaries. There are earthquakes that happen here on the divergent. They tend to be weaker than the other boundaries, and you definitely can have some strong earthquakes and weak ones on any of the convergent boundaries. And that was kind of the point of this worksheet here, where you plotted the depth and distance for all these earthquakes, is it kind of wanted you to notice that there were some features on the surface. So we have a trench, we have the Tonga Islands, we have all these earthquakes below the surface, and I drew my line of best fit. That kind of went down like this. And we had some questions that asked us a few things about this. So it says, use a ruler, draw the line of best fit, which I did. Is there a pattern for earthquake activity under the Tonga Trench? If so, what is it? So in general, the pattern is that the earthquakes from the Tonga Trench, that's where they're the shallowest or closest to the surface. But as you get further away from the Tonga Trench, they get deeper and deeper. Okay. So earthquakes get deeper as you approach zero. Think of the plate models you've observed in class. What do you think is causing the line of earthquakes beneath the Tonga Trench? All right. this is essentially how scientists know that like there is a plate sliding under another one. So they've looked at earthquake data at these trenches, and what they notice is they get slowly deeper and deeper. If you look at a convergent boundary like in the Himalayas, where there isn't a plate sliding under, they do not see these deep of earthquakes. They'd all be very, very shallow up at the surface of the earth. If you look at a transformed fault, a transformed boundary, they're all shallow. If you look at a divergent, like a mid-ocean ridge earthquakes that happen, they're all very shallow. So what this pretty much means is as that plate is sliding under, you're going to have parts of it that crack, that break, that snap off as it's melting, because it doesn't instantly melt. So what that shows us is we do have that plate. You can think of it as the plate coming in here, and it goes under the other one. Okay. So these earthquakes kind of let us see a plate when we clearly can't drill to it, we can't take a picture of it, anything like that. What kind of plate boundary do you think is shown in this activity? So if we have a trench, first of all, is one of our clues. If we have a plate sliding under another plate, if we have these Tonga Islands, which to me would be volcanic because of all these other things that is in the information here, that tells me I have a convergent. So the trench lets me know that there's a plate that's sliding under. Subducting is the fancy word for that. That lets me know that that's happening too. So based on what you learned from this activity, how would you define a trench? It's a deeper area of the ocean created or made when one plate slides under another. And then as oceanic plates sink into the mantle, it releases water that facilitates or helps melting. What surface feature is the result of rising melt? So the Tonga Islands are the cause of this, the result of this. They will be volcanic islands made from the melting magma. So that's kind of like the Aleutian Islands on Alaska. Okay. And then the very last one, we had to label a few things. So we're going to have trenches. I wish these arrows would have pointed in slightly different areas. They should have pointed like right here. That's where the trench is going to be. But given the options, that was the best one for that particular area. Spreading ridge, ocean ridge, same thing. So that's right in the middle here. Convection cells, where the warm magma rises, it drags the plates with it, then the cool sinks back down. We have the upper mantle, and then this chunk here at the very top that's closest to the crust is called the asthenosphere. So the question kind of asked, how do these convection cells help move the crust? So in the middle, you have the warmer magma rising. When the convection cell starts to turn at the top, it drags through friction, pretty much, the ocean crust away from the ridge. This causes the ocean crust to move towards the continental crust. Then the ocean crust subducts, so we've got two subduction zones on both sides under the continental crust. I guess I could have added that the cool magma sinks again there too. So that's kind of the explanation for pages 9 through 13. The only other thing, if we take a look at what you're going to have to do for the quiz today, apparently I closed out of it. So the quiz is going to have you draw pictures. However you do that, however you get the picture in this box, I don't care. If that is taking a picture of one that you hand draw, perfect. If it is using Google Drawings, or this one that I found today, which has got a little bit more features than Google Drawings, called Sketch.io, Sketchpad. What I notice is I've got a bunch of different tools I can use here. If you don't have a mouse, I don't think Chromebooks can even have a mouse. Oops, what am I doing? You can click and drag with this path one, or you can just hand draw it with a mouse pad using like a paintbrush or something like that. But if you want to make a plate and you want to have mountains, and you want to have a plate crashing into another one, you just got to draw and connect it. You can fill it with stuff. You can show magma. You can show convection cells. There's arrows that you can draw to show the way these plates are moving. So if it's moving away, towards, whatever you got to do. And then you can screenshot it. I don't know if there's a copy button here. Export. So you can save it possibly or share it. And you can also just do screenshot. And I'm assuming the Chromebooks have that function. For me, I can do that. Paste it in here. I can crop it so I don't have all this extra junk. Right. And then I can move on to the next one. Obviously, this is not a complete picture. You're going to want to have a picture similar to what you drew on pages 9 through 9 and 10. Those are the kind of pictures I'm looking for, not the before pictures, but what it looks like after the movements happen for a while. And then there's some things to highlight. That was the only way I could think of doing that. There's things to just write the letter of your option. So if this one's A, just put an A there. If this one's B, put a B there, so on and so forth. Otherwise, that's what you're working on today, is just finishing up that quiz. You've got 3 pictures to draw, 3 things to highlight for each of those pictures, and 8 questions that go off of this world map up here. So if you have any questions, feel free to shout out to me on GoGuardian or email. Either way, have a great weekend. Have a great spring break.